So first off, how many degreed engineers do we have in the audience? Oh, great. Then I'll really whip through this first part about what does duct pressure have to do with anything. But here's some learning objectives, and I hope we will be able to come back and say that we've accomplished all these. The agenda, I want to talk about duct static pressure and what its contribution is in lab energy. Talk a little bit about codes and standards. If you were here for the last session, you got a lot on codes and standards. But I want to relate that to static pressure control. A little bit on dampers and Venturi Air Valves, sort of the two technologies out there for controlling airflow in lab supply and exhaust systems, and how they interact with static pressure in the ducts. Then a little overview of three different methods for controlling static pressure, the fixed static method, sort of trial and error methods, I'll call it, and a model-based approach. I'll give you a little bit on one laboratory's experience with this model-based approach to dynamic static pressure control. And then talk a little bit about some research that's been done on coupling of airflows in connected terminal systems. It sounds more exciting than it is, but there's some integral signs and some simultaneous equations. We're all going to enjoy that. And then finally, we'll talk about dynamic static pressure control in exhaust systems. And just to give away the punchline, this is the real payoff for what we're talking about today. And part of that's because of where energy is used in laboratory ventilation systems. These numbers we pulled together from sort of a composite of about 4 different jobs where we were able to meter the energy in various parts of the HVAC system. And in round numbers, the supply fan accounts for about 50% of the energy used. The exhaust fan over at the other end accounts for about 20%. And in between, there's cooling, heating, humidification, reheat that use up the other 50% of the energy in the system. So the key here is that 50% of the utility in your HVAC system in your lab is literally going into the air. Also, if you know anything about fans, the energy the fan is expending comes from 2 components. So one is the airflow rate, how much air you're pushing through the fan, and the other is the pressure through which you have to drive this air. The 2 of those things together multiply to the fan energy. So if you've been to any of the other sessions, you've probably heard people talking about ventilation rates, right? What is it, 6 air changes or 4 air changes now? How many want 4? How many want 8? Okay. The whole key there is you're changing the ventilation, the airflow rates through the system, and you're doing a big job on reducing fan energy. But every time you reduce the flow through that fan, you have an opportunity to reduce the amount of pressure that you're also using. So this is a graph that's supposed to show you kind of what the pressure is going through the air handling system. There's some of this kind of work been done before with Labs 21, the low energy design guidelines. And basically each component in the air handling system has its own contribution to pulling away pressure, pulling away energy. And then the fan, of course, has to push that pressure back up to get it to push through the ductwork. All these elements that you see are sort of passive elements. They don't change their shape and size. So all the losses of pressure from the air going through there comes from friction effects. So the higher the velocity, the higher the flow, the higher the losses. So again, when we do all that air change rate reduction, we're saving energy and we're saving on needing static pressure. But you can see the air valve that's highlighted there. Those are the control elements that control the airflow rate through the individual parts of the duct system, and they're the thing that really end up doing the heavy work of killing off any excess static pressure that's coming from the fan. So I want to talk a little bit about the 2 big design elements that people use, either blade type dampers or Venturi Air Valves, and how they interact with static pressure. Essentially, you see these 3 lines. These represent those dampers there at fixed positions. The solid one that's marked minimum operating pressure drop, that's basically where the damper's wide open. And if you look at any cut sheets for a blade damper style product, you'll see them give you a minimum operating pressure drop graph or a table. And it's basically going to tell you to get a certain amount of flow through this device in the wide open position, how much pressure is needed. Now, how many, if you've got 20 terminal boxes connected to a run of ductwork, and you're pushing a certain amount of pressure in at one end, all those boxes, ideally, you'd like to have them operate wide open, at the absolute minimum. Unfortunately, that's not going to be the case. Probably you're only going to get one of them wide open. And so that's where the design point is typically. Also, when we're looking at this kind of a diagram, the line A there represents a constant pressure line. And if you've built a big duct system with a big manifolded connections, lots of little dampers connected to the ducts, to a big header, the actual pressure at that element, at that damper, doesn't change much when it moves. So the line A there kind of represents what the controller sees. But what we're trying to do too is figure out what we can do to reduce the static pressure that's being seen at the individual elements. And what that does, when they reduce the static pressure in the duct system, the damper has to open up. That's the red line B going down. Now what about Venturi air valves? You may know that Venturis are what they call pressure independent. You put it at a certain position that's indicated by the voltages here. These are actuator positions. Basically, the spring that's inside this cone is going to help offset the aerodynamic forces, and it's going to maintain a constant flow rate. So if you go to a higher pressure, that spring and cone are going to move and maintain the same flow rate as if you bring it down. But at some point, if you reach a minimum pressure drop, the spring is fully extended and the unit stops being independent. It just becomes another damper, and the airflows drop off at that point. So the problem is, unless you're measuring the flow through the Venturi air valve, you don't really know what the flow is. All you can do is measure the pressure drop across it to make sure that it's within its designed operating range. And then the static pressure optimization technique is basically have the air handling unit controller look at all those pressures and keep turning down the static pressure from the fan until one of the air valves is at its minimum point. So either way, whether it's a Venturi air valve or a butterfly damper or some kind of combination in between, we've got ways to control minimum static and still make sure that we're getting the airflow that we require. So this has been pushed by ASHRAE for many years. In the ASHRAE design handbook, people have talked about resetting the static pressure. Again, it's a natural phenomenon that falls out of the nature of fan curves. Other guidelines have pushed for it. And then in 2010, the ASHRAE Energy Guideline 90.1 explicitly stated that systems that have direct digital control of individual zones will have to start resetting that static pressure down until they're at the level where one zone is beginning to starve, basically. They put in explicitly stating until one zone damper is nearly wide open. So that's interesting to me. The guideline also sort of implies a control technique. Also, I just have to tell you, there's a lot of different numbers out there about how much you can save, and it really depends on all those other design factors. But I thought I'd just put a note in here that a lot of the people we've been talking to are seeing numbers like $300 to $500 per fan horsepower. It can be as much as 50% reduction in the fan energy compared to a fixed static pressure design. So these numbers, again, big fans, going to give you more savings. So it's good to look at this. So this is a little example of a small system. And first I wanted to talk about fixed static pressure control. This is what most buildings are doing. Even though the guidelines say do dynamic control of the static pressure, they're really controlling to a fixed static. And the idea there is that there's this pressure transmitter out here in the ductwork. Now, anybody know where that's supposed to be put? 2/3, right. The 2/3 is this thing. Anybody know where the word 2/3 came from? It just pulled, yeah, it's, exactly. It's, arbitrary is the nice word, okay. So in general, though, what you want to do is make sure it's not too close to anything. And of course, when you're a controls guy and you get to the job last, it's almost always the place that's least accessible. And you got to have a union pipe fitter running like stainless steel tubing someplace. I mean, that was always the stuff that was happening to me on jobs in New York. But that becomes the point at which we're going to control the whole system. So understand, this simplified way that we've been controlling static pressure for all these years essentially models that whole HVAC system, the whole network of ducts, as one point out there in that duct. Now, there's often a static pressure transmitter, or at least a switch here by the unit itself. You want to make sure you don't blow up the ductwork coming off the fan. And then the fan controller runs to a constant static. Now, how is that static pressure set on most jobs? Do we have any air balancers in the audience? Commissioning agents, guys who've done commissioning when they couldn't get a real job designing a building or something. Okay, so, sorry. Now, usually what happens is they open all the boxes up, and then they start bringing them back until they get to that maximum design point. And what's that maximum design flow? Usually it's the flow needed to cool that room on what's going to be ASHRAE's hottest day of the year. So the whole system gets designed for some day in August, and then, you know, when it's 10 degrees outside someplace, the system is running with enough static to cool the whole building down. And it's obvious, right? The system is designed that, you know, nature is dynamic, but this fixed system is not dynamic. And so therein lies the opportunity we have to do something better and save energy. Yeah, the hottest day. I wish it was hotter today. So static pressure reset, and I'm going to call this trial and error methods. Now, if there's anybody in the audience who has put their name on a static pressure design control method, I apologize. This sounds like I'm denigrating it, but really it's not. There's some very famous systems, trim and respond, some other things. But essentially what happens is that, again, there's this static pressure sensor out here, or maybe not. In most cases, we're using this sensor right here as the control sensor, the one by the fan. And the fan controller is getting information from the boxes, and it's trying to figure out, okay, is one of those boxes open? Remember what the standard said? Keep reducing your static pressure until one of the boxes is wide open. So it's going through this technique. Now, there's like 5 different techniques for how you get around to lowering it and how you make a step, and whether you make a big step or a small step, and whether you make a small step followed by a big step. Believe me, they're all out there. They've all been thought through, and they're well documented. And in the end, you're trying to find that one box that's open. Now, what happens if 2 boxes open? It's okay. We can all, you run the static pressure back up. Okay, that means that something else has changed in the system. So one interesting aspect of this kind of system of trial and error is that it's around the optimum point, but essentially it's never at the optimum point. And these techniques use lots of techniques to try to get close, but in the end, everything you're doing is still getting only close. You're always a little bit out of control. So that led people to think about other ways to do this, and one idea was what we call a model-based method. Again, we may or may not have a static pressure sensor out here. We might have one out there if there's a particular element we want to make sure it gets enough flow, maybe a Venturi Air Valve or something, but most all of it is done right here at the fan. And what we do is the fan controller is getting the airflow set points from the boxes, and it's using a model that was developed as if each box was at any given moment the critical box. And I'll talk a little bit more about that, but just think about it. If you knew that a given box was the critical box, you could essentially say to yourself, what does that mean? That means if it's the critical box and it's wide open, a small change in speed at the fan is going to cause a change in airflow at that box. But what happens to everything else in the system? Well, it turns out they don't really change that much. In fact, that's how this whole technique works, that you assume that the rest of the system ends up looking like this great big pipe here. That's what my blue thing is. It's like one great big pipe. And if you have one great big pipe, then you can model that just like an orifice. So you can say the pressure between the fan and the box is equal to the flow rate squared times some K factor. And you can do that if it's this box, or if it's this box, or if it's that box. Now, do you have time to go make sure every box goes to critical? No. Turns out, by the way, it's impossible. All the boxes can't go to critical. But how are you going to figure this out ahead of time? Well, and I guess I just ought to mention the fact that we're going to build this model based on this critical point pretty much ensures that this technique gets you to the optimum. You're not going to be around it. And what we do is we use basically a single line diagram to make sure we get essentially where all the boxes are in relation to each other, because you want to know about how these connect. You do that so that you can build a series of equations that relate these K factors and these pressures to all the different flow paths in the system. And then you get yourself some data from the system. It's commissioning, okay? And you were going to spend that time balancing the system anyway. So this instead is you go after it systematically, and you run airflow through the system with boxes in different combinations of being open and closed, wide open and closed. And the data sets are chosen so that you make sure you get a little bit of air and a lot of air at any one time going through each of these connections. And that data is used to build this mathematical model. Now, what's that look like in actual fact? Well, this is some data from a real customer in San Diego. And again, San Diego is a great place to test stuff. You should always go there. It doesn't get very cold. The customer started out, all of his systems were running at 2.5 inches of static, 9 air handling units, and they were all set to 2.5 inches of static. Why? Because it worked well on the one over there, so it's going to work well over here. We'll talk more about that logic. The day we implemented the system, turned it on, it was a pretty hot day in August, and we had the misfortune or whatever, the momentary surprise that the duct static pressure went up. The system, our magic system said, oh my God, you need more static pressure. But actually it turned out we did need more static pressure. While they were running at 2.5 inches, they were actually starving some of the zones, and some people were complaining. So, we said to the guy, look, you're the one that gave us the designs. The mechanical engineer that designed your building told us that he needed 1,000 CFM in zone 6, and you were only getting 900 CFM to zone 6. So now at the higher static, you're getting the right amount of flow there. So the customer agreed that that was right. And he really felt good about it when about 2-3 hours later, the system started going down in static. And so all summer long, it pretty much repeated this pattern. And even during the occupied periods, it was higher, but it was only higher momentarily, right? So all the space below that black line of 2.5 is basically energy saved. Luckily, the fall happened, and then the winter, and it saved a lot of energy during the cooler periods. And in fact, we got to see a lot of unoccupied conditions here when there was absolutely no load, especially weekends. There was tremendous savings here, right? So they'd been running at 2.5 inches, and they ended up running as low as 0.7 inches on the weekends. So, instantaneous savings of like 60%. And so it averaged out 30 to 50% over the last 2 years. Also, another interesting fact that you have with a model-based approach is that you can actually predict which boxes are going to be the ones that, based on their design conditions, are going to be the critical boxes. And so we were able to predict, and these are just some numbers, but I wanted to give you for comparison here. Like box number 5 and box 13 were predicted to be ones that at their occupied max flow settings would be the critical boxes. Boxes 12 and 14 were the ones that at their unoccupied flow settings were predicted to be the critical boxes. And then for about 4 days, we had box 13 that popped up as the controlling box. And I don't know how well you can see it. Basically, there's like 4 days of these blips are each a day. There's 4 days where there's no blip, where the system ran at constant static pressure the whole time. And I saw this data when they sent me the file, and I called them back and I said, what was going on those 4 days? And they said, oh, we were renovating this one space. I said, what did that involve? They said, well, we were knocking down the wall to make it a bigger space. And but we wanted the workman to be cool, so we just jacked up the set point on the controller, and it was running constant flow. And I said, just by dumb luck, you managed to pick the one box that when you ran it higher than your original design, right? Because it was like a 12-inch box in a tiny little room, and it was running a really low flow rate. But when they jacked it all the way up, it became the box that needed the most out of its model. Now, that was appropriate, by the way. They knocked down a wall. They had a room like this big being controlled by one box. So, okay, that was good. They kind of did the right thing without knowing it. But when they went back to it, they said, oh, great, this is great. We can figure this one out. And then I have to admit, my communication skills need some work. It was only after this that they recognized why I told them to look at the box numbers on the graphic, right? And so we're still working on how to use the information real effectively. But the whole idea here is that this model tells you more about how things are working, more than just the static pressure itself. Finally, my colleague Jim Coogan published a paper last year at ASHRAE where he took that same set of data from another project we did, and he went in and did some additional analysis. So our initial analysis, our model building technique, is it tells us which of these boxes are going to be the critical boxes. But I guess I like to look at this analysis and say, who's most likely to be second place? Who gets miscongeniality in this thing? So here's an example of a system that it's two branches from an air handling system, and Jim's analysis came up with a way to talk about the coupling factors between these, and it's probably on one level obvious once you see the data, but essentially you can see that all the boxes on 1 through 8 here, they're all on their one branch, and the darker the block, the more it's being impacted by that. Those two are impacting each other. And the dark lines going down the middle, that's the box itself impacts itself. That's how that works. So you can see that it basically is two separate systems. The boxes in this branch don't interact with the boxes in this branch. Why would this be important? Well, if we're talking about offices and classrooms and stuff like that, it's not that important. But this whole conference is about laboratories and critical spaces. And you did notice that 30% was supply, 20% was exhaust fan energy. And to my knowledge, there's almost nobody doing any kind of optimization on the exhaust fan, yet it represents 40% of the fan energy in a building. So if you're going to go after fume exhaust, you want to know something about how likely is a change in any other box going to affect the boxes that you think are critical. And I guess the key thing I want to let you know is that this model-based method it's robust, it's scalable, it has a lot more information than we even expected. So if you've got an exhaust system, you could be looking at dynamic static pressure control. Now, why haven't we done more of this in the past? Well, people just didn't like the idea of slowing the fan down. And what's the classic one? You come in on a Monday morning after a long weekend, and the exhaust system has worked its way down to the lowest possible static. You walk into the lab, you throw open the 8-foot fume hood that you have, and it goes into alarm because the big speed drive figures out that the static went down a little bit lower and something else needs a little bit of airflow, and pretty soon, the big fan starts speeding up, but in the meantime, you're standing in front of this 8-foot hood that's not getting enough airflow. And it only takes one or two of those events for somebody to figure out that they're just going to override that fan, right? Often override the fan to a higher setting than what they had before. We just all know how that works. So the idea here, the trial and error methods, they don't help you much because they don't have easy ways to include, like, this box is critical. Treat this box differently from the rest. They don't have built in any understanding of how one box differs from the other. They're just looking at opening and closing dampers. Or maybe they're looking at, are you short of your airflow set point? But you were right on your airflow set point when the flow was low because you had the sash closed. And within 1 second, you have to respond with that fume hood to get the airflow up. So how could we use the model-based approach? Well, one thing we could do is use occupancy sensors in the lab spaces. Someone walks into the lab, the occupancy sensor sees that, and it could tell the fan system, okay, now we're going to use a different rule. Instead of using the flow set point that's coming from the controller, this box that I'm looking at, it's a fume hood, and I want you to use the flow set point as if the sash was up at 18 inches. Now, on one level, it's a small thing. Another level, it's not the optimum, but it is a way to make sure the system has enough capacity waiting so that if someone comes in and opens that sash, they're going to get enough flow. If you got some of these big open office, open lab kind of concepts, then putting a presence sensor on a fume hood could get you the same thing. Or you could have a simple decision rule like, 7 a.m. every day. Or if anybody walks down the hallway, then we turn the airflows up. And again, I'm sorry, we're not turning the airflow up. we're turning the system exhaust capacity up. The system exhaust capacity won't actually increase that much because the main driver of cost is the airflow rate. So it's going to cost you more money when someone actually uses the fume hood. But in the meantime, you're going to be plenty safe. So finally, I just want to close with 2 slides that relate to what happens if we put a little more intelligence into the terminals. So remember this slide here. This is kind of a characteristic of a butterfly damper. And if you were able to program that into your box controller, then the controller would know when it was close or when it had too much pressure. And the controller itself could tell the main fan system, hey, I'm at 3 inches right now, 0.3 inches of water column, but I know that to make this 500 CFM set point, I only need 7.5 hundredths of an inch. So I can give you back 0.225 inches. And if the next box down says, I can give you back 0.1 inches, and the next box says, I can give you back 0.1 inches also, then the main air handler says, okay, I can take back 0.1 inches and everybody will be satisfied. And then the main air handling system could use that technique. All right? This is different than a box controller saying, hey, I'm starving, I'm missing my set point. This is different than a box controller saying I'm at 90% or 90 degrees. This is the system understanding itself. And I'll be honest, I think that's where most of this technology is going. But at the end of the day, it's going to take information from both sides, bottom up and top down. And the control systems we have today are sophisticated enough to do that. So at a minimum, start paying attention to your duct static pressure systems. And if you're not resetting them right now, do something simple, like when the building's unoccupied, turn the static pressure down. That's it.
Siemens, ingenuity for life.